Gasoline is one of the most critical fuels powering the modern world, moving cars, trucks, motorcycles, and machinery across continents every single day. Yet few people ever see the vast industrial system required to transform thick, black crude oil into the clear, highly refined fuel pumped into vehicles. Behind every gallon of gasoline lies one of the most complex chemical manufacturing operations on Earth, involving massive distillation towers, extreme heat, high-pressure reactors, precision blending systems, continuous laboratory testing, and non-stop safety monitoring. What appears to be a simple liquid is actually the final product of dozens of tightly controlled processes working together inside enormous oil refineries. And today on the How Factory, we're going step by step inside modern refineries to see exactly how gasoline is made from crude oil, from underground extraction to finished fuel ready for distribution. The journey begins with crude oil, a naturally occurring mixture of hydrocarbons formed over millions of years beneath the Earth's surface. Crude oil is extracted through drilling operations on land and offshore, then transported to refineries by pipelines, ships, or rail. When crude oil arrives at a refinery, it is anything but uniform. Different crude sources vary widely in thickness, sulfur content, and chemical makeup. Before processing begins, samples are taken and analyzed to determine the crude's composition. This information is critical because refining parameters must be adjusted depending on whether the crude is light or heavy, sweet or sour. Once approved, crude oil enters the refinery and is pre-treated. The first major step is desalting, a critical process that removes salt, water, and sediment. Crude oil is mixed with fresh water and passed through electrostatic separators that cause water droplets to merge and fall out, carrying salts and impurities with them. Removing salt is essential because salt can corrode equipment and poison catalysts used later in refining. After desalting, the crude oil is heated in large furnaces to temperatures exceeding 350 degrees Celsius, preparing it for separation. The heated crude oil then enters the atmospheric distillation unit, the heart of the refinery. This towering steel column, often over 40 meters tall, separates crude oil into different fractions based on boiling point. As the hot crude enters the base of the tower, it begins to vaporize. Lighter hydrocarbons rise upward, while heavier components fall downward. Inside the column, trays and packing materials help control vapor flow and condensation. At various heights, different products are drawn off. Gases at the top, followed by gasoline-range hydrocarbons, kerosene, diesel, and heavier oils. This process does not chemically change the oil, and it simply separates it. The fraction that will eventually become gasoline is called naphtha. However, straight-run naphtha from distillation is not suitable for modern engines. It lacks the proper volatility and octane rating required for efficient combustion. To transform it into usable gasoline, it must undergo several additional refining processes that rearrange its molecular structure. One of the first upgrading steps is catalytic reforming. In this process, naphtha is sent into high-pressure reactors containing platinum-based catalyst. Under temperatures around 500 degrees Celsius, the hydrocarbon molecules are reshaped into more complex structures. This increases the octane rating, allowing gasoline to burn smoothly without engine knocking. Reforming also produces hydrogen, which is captured and reused in other refinery processes. The output of this unit is a high-octane blending component essential for gasoline production. Another critical process is fluid catalytic cracking, often referred to as FCC. Heavy hydrocarbon fractions that are too large for gasoline use are fed into FCC units where they are exposed to extreme heat and powdered catalysts. The molecules crack into smaller, lighter hydrocarbons suitable for gasoline and diesel blending. The catalyst continuously circulates through the system, being regenerated by burning off carbon deposits. FCC units are among the most active and visually dramatic parts of a refinery, operating non-stop and producing large volumes of gasoline-range material. Hydrocracking is another upgrading step used especially for heavier crude oils. In hydrocrackers, heavy hydrocarbons are mixed with hydrogen and passed over catalyst under high pressure and temperature. This process breaks molecules apart while also removing sulfur and nitrogen impurities. Hydrocracking produces very clean gasoline components along with jet fuel and diesel. The hydrogen-rich environment helps produce fuels that meet modern emission standards. Throughout these processes, sulfur removal is essential. Crude oil naturally contains sulfur, which must be reduced to extremely low levels. Hydrodesulfurization units treat gasoline components by reacting them with hydrogen over catalyst, converting sulfur compounds into hydrogen sulfide gas. This gas is then processed in sulfur recovery units to produce elemental sulfur, which is sold for industrial use. Removing sulfur protects engines, reduces air pollution, and ensures regulatory compliance. Once individual gasoline components are produced, the refinery enters one of the most precise stages: blending. Gasoline is not a single substance, but a carefully engineered mixture of hydrocarbons and additives. Blending systems combine reformate, cracked gasoline, alkylate, isomerate, and other components in exact proportions. Each blend must meet strict specifications for octane rating, vapor pressure, energy content, and emissions performance. Computer-controlled blending systems adjust ratios in real time based on laboratory feedback. Additives are also introduced during blending. These may include detergents to keep engines clean, corrosion inhibitors to protect fuel systems, antioxidants to prevent degradation, and anti-knock compounds. Seasonal adjustments are made as well. Summer gasoline is formulated differently than winter gasoline to control evaporation and emissions in varying temperatures. Each batch is tested repeatedly to ensure compliance before it leaves the refinery. Quality control is constant. Refinery laboratories operate around the clock, analyzing fuel samples using advanced instruments. Technicians measure octane ratings, density, sulfur content, vapor pressure, and distillation curves. Even slight deviations can cause performance issues or regulatory violations. If a batch fails testing, it is reblended or reprocessed. After blending and approval, gasoline moves to storage. Large tank farms store millions of gallons of finished fuel in floating roof or fixed roof tanks designed to minimize vapor loss and contamination. These tanks are monitored for temperature, pressure, and volume. From storage, gasoline enters the distribution network. Transportation is the final step in the journey. Gasoline is moved primarily through pipelines to regional terminals. Pipelines operate continuously, pushing batches of different fuels separated by interface zones that are later reprocessed. At terminals, additional additives may be injected to meet local requirements. Tanker trucks then deliver gasoline to individual gas stations, where it is stored underground until pumped into vehicles. Behind the scenes, refinery operations are tightly controlled for safety and environmental protection. Refineries contain thousands of sensors monitoring pressure, temperature, flow, and chemical composition. Automated shutdown systems activate instantly if abnormalities occur. Workers undergo extensive training, and facilities are designed with multiple containment layers to prevent spills or leaks. Environmental systems are integral to modern refineries. Wastewater treatment plants clean water before reuse or discharge. Air emissions are scrubbed and filtered. Heat recovery systems capture energy from hot process streams to improve efficiency. Many refineries operate cogeneration plants that produce both electricity and steam, reducing overall energy consumption. What makes gasoline production remarkable is the scale and precision involved. Refineries process hundreds of thousands of barrels of crude oil every day, yet the final gasoline must meet exact chemical standards to perform reliably in millions of different engines. The transformation from thick crude oil to clear, high-performance fuel requires chemistry, physics, mechanical engineering, and automation working together seamlessly. From underground oil reservoirs to towering distillation columns, from cracking reactors to blending manifolds, the journey of gasoline is one of the most sophisticated industrial processes ever developed. Every acceleration, every commute, and every long drive depends on this hidden system operating flawlessly day after day. And that is exactly how gasoline is distilled, cracked, reformed, cleaned, blended, tested, stored, and delivered from crude oil inside modern refineries. A powerful demonstration of industrial chemistry and engineering at massive scale. Thanks for watching the How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, processes, and factories that power everyday life.